The topic we are going to talk about today is on the screen, trig integrals. We just call them trig integrals. Okay. I will show you what we are going to do. If you look at the handout, part 2, we did part 1 last time. In part 2, you have integrals like those, in which the integrand are trig functions, are all kinds of trig functions, multiplication and radical and stuff. Okay. Yeah, the main thing today we're going to do is to talk about how to evaluate these integrals. Again, in which the integrand has many trig functions. We're going to classify different types, and then we evaluate. So, but before that, I want you to take a picture of the screen. On the screen, you have many trig identities. Trig identities you need to memorize. I want you to memorize. At this point, you just take a picture of the screen. You have many trig identities. These trig identities are very useful for evaluating an integral in which there are many trig functions. The first one has two alternative forms. One alternative form is sine of x squared is equal to 1 minus cos of x squared, the whole thing squared, I mean. Okay. And the other alternative form is cos of x squared, the same thing, right? Is equal to 1 minus sine of x, the whole thing squared. The second formula, I want you to know one alternative form. The alternative form is tan of x squared is equal to secant of x squared minus 1. The third one has alternative form cotan of x squared, the whole thing squared. Of course, these are trig identities. X can be replaced with u with whatever thing. Okay. Cotan of x squared is equal to cosecant of x squared minus 1. Okay. The first few questions we are going to concentrate on how to use these three formulas to evaluate the integrals. In most cases, the questions are in the nature of using the substitution rule. Okay. Take a picture of the screen. Okay. And then we'll start from the first question. I meant on this screen, sorry. Later on, I'm going to summarize for which type of the integrals we can use the trig identities to evaluate the integrals. But for this question, the trick is to write the given function, write the integrand sine cubed of x, sine of x, the whole thing cubed. Okay. The idea is to write this function as the product of two functions. We'll see what's going on later. Okay. For this one, I want to rewrite sine of x, the whole thing cubed, as sine of x squared multiplied by a sine of x. So basically, we leave out a factor of sine of x. Again, very shortly, I'm going to summarize the form of the integrals to classify the integrals for which we can evaluate. Okay. And then we are going to use the trig identities, one of the trig identities, to handle that term. Now let's recall, I just told you sine of x squared can be written as, it's here, sine of x squared can be written as 1 minus cos of x squared. We'll see what's going to happen in the next integral. Okay. Now we'll rewrite that factor in terms of, we use the trig identity. Okay, we use the trig identity, we write that factor as 1 minus cos of x, the whole thing squared, and then sine of x, and then dx. Okay, I told you earlier, for almost all the questions we need to use the substitution rule. Okay, anybody want to tell me the substitution at this point after I apply the trig identity? Anybody want to write in the message what trig substitution I need to use? Now let's recall what I told you before. To use a substitution, the key is to choose u. That may not be working. The key is how to choose u, so that one function can be written as a function of u with easy to compute antiderivative. The other function is the derivative of u times a constant. We treat the integrand as the product of two functions. Choose u so that one function can be written as a function of u with easy to compute antiderivative. The other function is the derivative of u times a constant. Okay, u cos of x will work. Okay. Now let's say if we set u to be cos of x, then one function will be a function of u, can be converted to a function of u as 1 minus u squared. We know how to get antiderivative of 1 minus u squared. One function will become a function of u with easy to compute antiderivative. The other function is the derivative of u times a number. Sine of x is the derivative of cos, not exactly, multiplied by -1. Right? That's how this u will work. Okay, we follow the routine. Now let's recall, after choosing u properly, and then we compute the differential of u. Right? We follow the routine. All the questions are the same. You follow the same steps. We compute du. Du is the derivative of cos of x is negative sine of x, and then times dx. Right? We just did the differential of u. Right? The integrand is the product of two factors. One factor will become a function of u. The other factor, together with dx, you imagine a box. You put the other function, so together with dx, in the box. That's imaginary box. Okay. And then from the differential, if you choose u properly, the stuff in the box, you treat the box as a whole. The stuff in the box can always be written as a number times du. Okay, so in this case, I still want to write one more line. Sine of x dx, the stuff in the box can be written as a number times du. You divide two sides of the equation by -1, you have negative du. Right? Now we are ready to rewrite the integral entirely in terms of a new function of u. We start from here. Okay. This integral, you look at that line, so do not look at that line. Okay, this integral can be written as a new function of u, as everything is going to be in terms of u. We're going to change everything to u word. Okay. the integral of 1 minus cos of x, the whole thing squared, will be converted to 1 minus u squared. Cos of x is u, right? And then the whole thing in the box is negative du. And then this is a polynomial of u, which should be super easy to evaluate. Eventually you write the final answer as a function of u. So we're done, right? Now let's do that first. Okay. Negative antiderivative of 1. So do not write x. I know antiderivative of 1 is x in the formula, but here we are in the u world. Okay, everything is in terms of u. So this antiderivative of 1, it should be u, and then minus antiderivative of u cubed, u squared. I mean, okay, antiderivative of u squared is u cubed over 3. The power, right? After getting rid of the integration notation, we plus c. Okay. Finally, you need to write the final answer as a function of x, in terms of x. I mean, okay. You have negative. The relation between u and x is here. U becomes cos of x, right? Minus, on top you have cos of x, the whole thing cubed. So be careful the notation. This notation means cos of this notation. It means cos of x, the whole thing cubed. Do not write this exponent of 3 in here. It's wrong. Over 3, and then plus c, and then we're done. Okay. Any questions about this? That's how the trig identity is useful. In this case, we leave out a factor of sine of x, and then we use the trig identity, so the whole thing will work. Represented by this question, I'm going to summarize a tab. After this, I will let you try a few questions. Okay. Actually, the target is to rewrite the function in that form. I mean, rewrite the integral in that form. Okay. In the integral, you have two factors. One function is a function of cos of x. The other function here is sine of x. Okay. Okay. Summary. I'm going to add many forms on this page. Use a trig identity to convert an integral in the following form. Can I add something? If we can use a trig identity to convert an integral in the following form, then I'm going to tell you the form. I will tell you the trig substitution. The first form we have just seen is it's probably not in the textbook, so this is kind of my way. You convert the integrand as the product of two functions. One function is going to be sine of x, as we have seen, right? So the other function is going to be a function. I'm going to use uppercase F to denote a function of cos of x. Or alternatively, you just interpret that factor as a function in terms of cos of x. If a function can be converted to that form, you need to memorize many trig identities. You need to be able to see what trig identities you need to use to do the conversion. If integral can be converted in that form, and then it's possible to evaluate the integral. I'm going to write the trig substitution you need in this case. Anybody want to look at your notes? Now look at your notes, please, to tell me for this form what trig substitution we need to use. We set u to be cos of x, so like we just did, right? Cos of x. Yeah, that's correct. Cos of x. That's one of the class. Again, now we're learning integration techniques. We're going to classify many types of the integrals for which how to evaluate. So that's the idea. Likewise, I believe you can imagine the next class. I will let you try some questions in the next form. The next form is I believe you can imagine. You just replace the location of sine and cosine, and then you have the other form. The integrand can be converted to the product of two functions. One function is going to be a function in terms of sine of x. So the other function is a function, let's say cos of x. In many cases, you leave out a cos of x. Okay? Can make the thing a little bit more complicated. You could even add a constant of k in here. Essentially the same thing. I'm going to add a constant k in here. Actually, k can be any constant. K is not necessarily a whole number, a natural number. K can be any real number, actually. In this case, if an integral can be rewritten in that form using trig identities, and then the substitution we need, I just write u in here. Okay, the substitution we are going to use is u equals. Now take your best guess, please. The first case would be kx. Yeah. In this case, it would be sine of kx. Okay, sine of kx. Okay, now we are going to move on to question 2. After that, I will give you some additional questions to try. Okay. We'll move on. Okay. For an integral like this, in many cases, you just leave out either sine of x or cos of x. How about I'm going to modify the question a little bit to see if we can do it too. Okay. Can I add a factor of 2 in here? Add a factor of 2 in here. Maybe we could use brackets here. Apparently, the brackets are not essential in terms of the convention. But the integral is. I'm going to rewrite the integral to make the meaning clear. Okay, we are trying to evaluate sine of 2x, the whole thing squared, times cos of 2x, the whole thing cubed. We evaluate that. Okay, now look at the forms. I believe you can see that's the second form. You leave out a factor of cos of kx. You leave out a factor of cos of kx. I don't know what questions to ask you, but I think you got the idea. You leave out a factor of cos of 2x. and then your target is to rewrite everything else as a function of sine of x. I'm going to copy the integrand. Okay, sine of 2x, the whole thing squared. After leaving out cos of 2x, you have cos of 2x, now the whole thing squared. Right. Again, in many cases, you think about leaving out either a sine of some x or cos of some x, and then you write the other factor as in terms of. So in this case, we leave out cos of 2x. I want to rewrite the other factor in terms of sine of 2x. Right. Anybody want to tell me what trig identity we can use to achieve that? Is it possible? Okay, we left out a factor cos of 2x. Is it possible to write the whole thing double underlined in terms of sine of 2x? If we can do that, then it's possible to evaluate the integral. Anybody want to write the trig identity I need to use to achieve that? So please, write something in the chat. What trig identity? Yeah, the trig identity we need to use is this factor, cos of 2x, the whole thing squared, can be written in terms of sine of 2x, the whole thing squared. Okay. And by the way, the trig identities I just reviewed, this x can be replaced with anything. In particular, in this form, the following trig identity will also be true. So cos of x can be replaced with u, with anything actually. Cos of 2x, the whole thing squared, can be written as 1 minus sine of 2x, the whole thing squared. I hope it's not too hard to understand that. The trig identity, you just imagine 2x as u. Okay. All right. Using the trig identity we just mentioned. Again, our target is to write the double underlined part in terms of sine of 2x. So this one is already sine of 2x squared. We do not have to do anything about that, right? And then using the trig identity, cos of 2x, the whole thing squared, can be written as 1 minus sine of 2x, the whole thing squared. I don't know how much trig identities you have learned in high school, but I think it's you should have learned that after last March or something. It's probably you don't have much school at that time. I hope at least try to memorize the trig identities. Okay. And then that's cos of 2x. You see, we have achieved the form. The form is one factor is a function of sine of 2x. The other factor is cos of 2x. Now, essentially, we have that form already. The second form, I mean. Okay. Still, before we do the substitution, I want to add one more step. Now the double underlined part is essentially a polynomial. How can we see that? You multiply them out. Multiply them out. I think you have sine of 2x squared minus, you multiply them out. Okay. Sine of 2x, the whole thing to the power of 4. I believe you can follow me now. You multiply them out. Essentially, you have a polynomial of sine of 2x. I just copied the other factor together with dx. Earlier I told you if you can achieve this, again, if you can achieve that, you can write the integrand as the product of two factors. One factor is a function of sine of 2x. The other factor is cos of 2x. In this case, then we can use a substitution to make the whole thing work. Now tell me the substitution, please. Tell me the substitution, please. And probably I can squeeze it here. Tell me the substitution, please. Let u be. I told you earlier, it's in your notes. Let u be sine of 2x. Okay. Yeah, that's right. In general, if you can convert the integral to that form, the substitution you need is let u be sine of kx, in this case 2x. You're going to see how it works. Okay. And then the routine is we compute du, right? We compute du. Du is the differential of u. The differential of u, we take the derivative of that. Do not forget chain rule. You are going to use chain rule here. Okay. Using chain rule, I think you have 2 cos of 2x. At this point, I'm not going to review too much about the chain rule. If you still have trouble with the chain rule, review Math 101. Review your notes, please. Okay. That's du. Okay. Your imaginary box is here. The other function together with dx is your imaginary box. Imaginary box is here. Solve the imaginary box as a number times du. So cos of 2x dx is equal to half of du. After that, we are ready to convert everything in terms of u, right? In the u world, we have this is nothing but u squared. The relation between u and x is here. Wherever you see sine of 2x, you write u. So minus u to the power of 4. And then cos of 2x. Sorry, I told you do not write two variables in one integral. What I meant is to write half of du. Cos of 2x dx. Cos of 2x dx is half of du, right? I still prefer to use brackets. I know many people do not use brackets in this case, but I still prefer to use brackets. Okay, you see it's essentially a polynomial of u with a degree of 4. It's super easy to evaluate. You just use the power rule. Okay, half of antiderivative of u squared. I think you have u cubed over 3 minus antiderivative of u to the power of 4. You have u to the power of 5 over 5, and then plus c. Okay. Eventually, we convert everything as a function of x. Convert the whole thing as a function of x. You are going to get half of u is sine of 2x, right? Can I just simplify a little bit from here? You multiply 1/2 in, I think you have 1 over 6. You have 1 over 6. And then times u to the power of 3 in terms of x. It's cos of 2x to the power of 3. I could write this one as on the numerator. It doesn't matter. The same thing. And then minus 1/2 times 1 over 5. I think you have 1 over 10. On denominator you have 10. The sign here is minus. And then u to the power of 5 in terms of x is cos of 2x and then to the power of 5. I think I did many things wrong. Wherever you see cos of whatever thing, you should replace cos with sine. Okay, I will correct that. Sorry, it's not selected, I don't know. I will start over, okay? You have 1 over 6. I think u is sine of 2x. You have sine of 2x, the whole thing cubed. Minus, on denominator you have 10. On numerator you have sine of 2x, the whole thing to the power of 5. Is that right? After getting rid of yeah, you still need to plus c. I hope it's not too messy. You got the idea. Any questions about this? Essentially, that's the whole idea. That's part of the thing we're going to do today. We're going to use to summarize some forms, and then we're going to use the trig identities to convert the integral to the required forms, and then we make the substitution, right? Then we're done. The next question is going to be an in-class quiz question. I want you to do question number 4. I will give you enough hint, but I'm not going to give you the complete solution to the question. For question 4, anybody want to tell me what factor you want to leave out? We want to write the integral in one of the two forms. I'm telling you the question is in the nature of one of the two forms. There's no way for you to leave out a factor of sine of x. Anybody want to write something in the chat? That's probably not what I meant. My question was you leave out a factor. What I'm trying to say is we rewrite the integral in the following form. You look at here, you have a cos of x, the whole thing cubed. I want to leave out a cos of x, so that cos of x is one of the factors. And then I want to rewrite the other factor, everything else, as a factor which is a function of sine of x. After leaving out a cos of x, the first step is to rewrite the integral in this form. Cos of x, the whole thing cubed, and now can be written as cos of x, the whole thing squared. So because you leave out a factor of cos of x, right? And on denominator, we still keep the form of the denominator. I mean. That's the first thing we do. Okay, now look at the form. That's what I meant by leaving out a cos of x, leaving out a factor of cos of x. What do we do next? The next job is to use a trig identity to rewrite the other factor in terms of sine of x. Is it possible? Cos of x squared can be written in terms of sine of x as 1 minus sine of x, the whole thing squared. I will show you what I mean. Okay. Again, that's an in-class quiz. In-class quiz question. And by the way, the folder has been created. I didn't forget that. Okay. The next thing we do is to rewrite the whole thing as a function of sine of x. So on denominator, you already have a function of sine of x, right? Now all we need is to convert the top in terms of sine of x. So you have 1 minus sine of x, the whole thing squared. There's nothing you can do about the denominator. Actually, you do not need to do anything about the denominator at this point. Right. At this point, we have converted the integrand to the form we want, or we have converted the integral to the form we want. Now let's recall, we wanted to convert the integral to the form that one factor is a function of sine of x, the other factor is cos of x. It's just cos of x. It's here, right? One factor is a function of sine of x. It's in terms of sine of x. The other factor is cos of x. In the question, we had the k value of 1. Right. At this point, you are ready to do the substitution. After getting the function in the form we want, we are ready to do the substitution. We set u to be sine of x, so in this case, right? And then we follow the routine. The differential of u is cos of x. The derivative of sine of x is cos of x. Then we write everything in terms of u now. We write everything in terms of u now. Okay. Now the given integral. So can I just go from here? It's probably simpler. This integral we keep on writing. Okay. This integral in terms of u. In terms of u is going to be. Sorry, I don't feel comfortable to do that. I will still write everything properly. Properly, I mean, okay. Whatever I write improperly, you could do it improperly. Now for the given integral, you look at here. You look at here. This integral is essentially the same thing as that. You look at that. Okay. It's equal to, you look at that, okay. Wherever you see sine of x, you replace sine of x with u. I think on the numerator you have 1 minus u squared. On the denominator you have square root of u, right? And then cos of x together with dx is du, right? What do we do next? What do we do next? Essentially, the whole thing can be written as sum or difference of radical functions of u. If you have trouble in here, then you probably have issues with their high school math. I will give you the next step. Okay, you know 1 over square root of u can be written as u to the power of negative 1/2, right? I was writing 1 over square root of u as a power function of u to the power of negative 1/2. And then you copy the numerator, you have 1 minus u squared. You should really be able to handle this using high school knowledge. Okay, and then you multiply them out. I will tell you one more step. Okay, probably on the assignment I will give you a few more questions like those, so you can get over it. You multiply them out. That factor times u to the power of 1/2 times 1 is equal to u to the power of negative 1/2. How do you multiply? That's my scratch paper. Okay, how do you multiply u to the power of negative 1/2 and then times u squared? It equals u to the power of something. Can anybody tell me the exponent? Write the thing in the message, please. We multiply two exponentials with the same base. You add exponents. You do not multiply. You add. You add. The property I'm talking about is a to the power of m, and then times a to the power of n is equal to a to the power of m plus n. Remember that? Okay, it should be 3 over 2, I believe. 3 over 2, right? I think 3 over 2 is right. Okay, at this point, I believe you can move on at this point. You know how to use power rule to integrate so both of factors, and then after getting the final answer, wherever you see u, you go back to x. Okay, the relation between u and x is here. I will stop here. Okay, I will give you a little longer time to complete the solution. Essentially, the questions in this section are in the nature that trig identities together with the substitution. We'll summarize many forms. We'll classify many integrals for which we can use the technique. Now I want you to complete the solution on your own. I'm not going to move on with that question. Okay. Or we could take a longer break later, and then you do the questions during the break. Can I move on now? That's enough for the integrals with many sines and cos. Okay. Now we are going to move on to get some other types. Okay. How about I'm going to add more types into the summary, and then we try questions. The third type, I believe you can guess. Now, for instance, in the second type, you write the one factor as a in terms of sine of kx. So the other factor, sorry, yeah, I think Tyler sort of wrote the answer on the screen you could compare it with your answer. Okay. But now I want to move on. So you do not have to finish the question. I will give you time to finish, but now I want to move on. Okay. I want to summarize the other type. One factor is in terms of sine, so the other factor is kind of the derivative of sine. Okay. Motivated by that, we are going to have one other class we are classifying. Right. The other class is to use the trig identity to do something to convert the integral to the following form. The following form is one factor is in terms of, now let's say, tan of x or tan of kx. Tan of kx. Anybody want to tell me the other factor? So just compare the thing with that. The other factor should be secant of kx, not the whole thing squared. So because the derivative of tan of kx is a number times secant of kx, the whole thing squared, right? That's another type.
So in that scenario, u would equal tan kx, correct?
Yeah, that's correct. That's correct. In this case, in this scenario, the substitution we need to use is u equals tan of kx. We'll see how this works. We'll look at. I will see if we have a question in that nature. Probably we do. I'm pretty sure question 3 is in that nature. Now look at your notes to see the form. In this case, we want to leave out a factor of secant of x, the whole thing squared, right? And we want to write everything else as a function of tan of x. What I meant is to rewrite the integral in the following form. Everything else is going to be in terms of tan of x. We just write everything already in terms of tan. We do not touch that. Okay. How do we handle the underlined factor? Anybody want to guess how we handle the underlined factor? We write the underlined factor as secant of x squared times secant of x. I said secant, why do I write cosine? Secant of x squared and then times secant of x squared. Now look at the double underlined factor. Is it possible to rewrite the double underlined thing in terms of tan? Now look at the formula including trig identities. Secant of x, the whole thing squared, can be written as 1 plus tan of x, the whole thing squared. We mentioned the trig identity earlier, right? What I meant is the integral of tan of x to the power of 6. You do not touch that. And then the double underlined, double underlined can be written as, now look at the trig identity as 1 plus tan of x, the whole thing squared, right? I still double underline that to indicate they are equal. You still have to copy secant of x, the whole thing squared. Now we kind of achieved the form we want. the integrand now is the product of two factors. One factor is in terms of time. The other factor is secant of x, the whole thing squared. Now look at here. One factor is a factor of tan of one factor is a function of tan of x. It's in terms of tan of x. The other factor is secant of x, the whole thing squared. That's the form we want. I think Ben told me the substitution. In this case, I'm going to continue on later, but I want to write the substitution here. So what's the substitution again? I think u equals tan of x. So Ben just told me. Okay. The reason is the derivative of tan of x is secant squared of x. Now your imaginary box is here. Imaginary box is here. Right? Now we are ready to be in the u world, okay, to convert everything in terms of u. Tan, wherever you see tan, you convert tan, you replace tan with u, okay. So you have u to the power of 6, and then 1 plus u squared, and then here secant of x, the whole thing squared, is written as du. You see we have converted to the integral of a very simple function, essentially a polynomial. After one more step, we multiply them out. The integrand is essentially a polynomial of u. So do you have u to the power of 6 and then plus u to the power of, anybody want to tell me, Eugene? So tell me this number. So tell me this number, please. So write down this number, please, Eugene. 8 is right. 8 is right. It's not 12. 8. Okay. 8 is right. U to the power of 6 times u squared. You have u to the power of 6 plus 2. Okay. So here you have u to the power of 8. 8 is right. Okay. Use brackets here. Again, so probably it's not quite wrong if you do not use brackets, but to me, it's not clear. Okay, at this point you can finish this. So the answer is going to be u to the power of 7 over 7, right? And then plus u to the power of 9 over 9. After getting rid of the integration notation, plus c. So the final answer is going to be, wherever you see u, you replace u with tan of x. So you have tan of x, the whole thing to the power of 7 over 7, and then plus tan of x, the whole thing to the power of 9 over 9, and then plus c. I hope I got everything right. I did not mess anything up, I think. That's how it works. I told you one other form. Any questions about this? Any questions? If you don't, I'm going to give you more forms. So, but I may not give you too many questions. But I will include more forms. I will see if we have time to. If I can make up some questions in more forms. Of course, so corresponding to this, you have number 4. Number 4 is going to be wherever you see tan of kx, you replace the thing with cotan of kx. Cotan of kx. One function can be written in terms of cotan of x. So the other factor, anybody want to guess? here, it would be the derivative of cotangent of kx. It's kind of cosecant of kx, the whole thing squared. So because the derivative of cotangent is equal to cosecant squared, in this case, the substitution you need is let u be cotangent of kx. I really do not think you need any question in that nature. Okay. So maybe two more tabs, or one more tab. Tab 5. The integral is going to be an integral in that form. If we have time, we'll cover. We're going to do at least one question in that nature. Okay. Now let me give you the form first. Okay. The form is the function can be written in terms of secant of x, secant of kx maybe, and then the other factor, the whole factor, is written in terms of kind of the derivative of secant of x, secant of kx, and then times tan of kx, which is the derivative of secant of kx times a constant, so times a number, right? Whatever number, we don't care too much about the constant at this point. And then u equals, in this case, the substitution you need is secant of kx, I think. You see, we are trying to classify the integrals, and for each class, we are going to talk about what substitution we need to evaluate the integral. Maybe one more class. Now you can guess. Replace secant of x with the cosecant of kx. And then the other factor can be written as cosecant of kx times cotangent of kx. The substitution you need is u equals cosecant of kx. Now I made up a question on the screen. The question is in the nature that you need to convert the integral to the second and last form I mentioned earlier. I meant that form. You could try to convert the integral to the form in item number 3, but it will not work. If one form is not working, then you can try to think about some other form. Okay. The idea is to leave out secant and tan, a factor of secant tan. I did not say the functions. The full sentence is you leave out secant of 5x together with tan of x. Okay. What I meant is to rewrite the integral in the following form. In the form of so now let's say you leave out tan of 5x times secant of 5x and then For all the rest, I want to rewrite all the rest in terms of secant of 5x. That's not part of the solution. I was trying to record the form for the particular k value of 5. Is it possible? After leaving out secant tan, the integral can be converted to after leaving out one secant and one tan. So this factor becomes tan of 5x, now the whole thing squared, right? And then times secant of 5x, the whole thing squared. Originally you had to the power of 3, right? You leave out the secant of 5x, and then times tan of 5x. Okay, so the given integral is equal to what I just wrote, the converted form. Now for the underlined factor, now look at the form. I want to write the underlined factor entirely in terms of secant of 5x. Is it possible? This factor has already in terms of secant of 5x. Now all we need is to do something to convert this factor in terms of secant of x. Now look at the trig identities on your phone. I told you to take a picture of it, right? Yeah, that's right. Okay, tan of 5x, the whole thing squared, can be written, you just treat 5x as u, can be written as secant of 5x, the whole thing squared, minus 1. And then secant of 5x, the whole thing squared, right? dx in here. Sorry, I did something wrong. Let's start over. Times tan of x, tan of 5x, I mean. At this point, we can choose a substitution, and then we continue. Okay, I'm going to remove that. Did I remove everything? Actually, I just wanted to remove that. That's what I wanted. The substitution part, I'm going to rewrite the substitution part in here. Okay. You know the substitution for this tab. We set u to be secant of 5x, right? And then we compute du. Du is equal to the chain rule. You see the chain rule here again. The derivative of secant of u is equal to secant of u times tan of u. When I said u, I meant 5x. Sorry, I was mentioning I was using one notation for two things, but I'm not going to write this u. It doesn't matter now. Okay. Anyway, the derivative of secant of 5x is secant of 5x and times tan of 5x. So do not forget, you have to use the chain rule. You have a number of 5 in here. Okay, now your imaginary box is here. Your imaginary box is 1/5 of du. I will still write that down. Okay. Secant of 5x and then times tan of x, tan of 5x, your imaginary box. I forgot to write du. dx. is 1/5 of du. You're right, I forgot that factor. Sorry about that. I forgot that factor, so can I add the factor to here? There should be a factor of secant of 5x the whole thing squared. Right? Now we're ready to convert everything in terms of u. So chat is right. I'm going to leave out 1/5, okay, out of the integration notation, and wherever you see secant of 5x is u. Okay, so here you have u squared minus 1 and times u squared. Secant of 5x the whole thing squared is u squared. Now the whole thing in the box is 1/5 of du. I will give you one more step, and then I'm not going to finish this. I believe you can handle the rest. In one more step, we are going to convert the integrand to a polynomial of u, for which we can use the power rule to get antiderivatives, right? I think that this one you have u to the power of 4 minus u squared, is that right? Multiply them out. I will stop here. I believe you can go from here. Okay. I'm going to write dot 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 to indicate you have a few more steps, but I believe all of you guys can handle the rest. So good enough. Any questions about this? If you don't, well, that's actually one tab. I just call them one tab, or one class of the integrals. In this one class, we have many subclasses. Okay. The other tab we are going to use is to handle other integrals. We'll start from. How about we start from question number 6? As long as you can do 6, then you can do 5. Okay. So we'll just do number 6. Probably that's right, Tyler. Okay, now look at number 6. Now look at the question on the screen. In some cases, if you see sine of whatever x or cos of whatever x to some even power, I said even power. By even, I mean the counting numbers like 2, 4, 6, 8, 9, right? So these numbers are even numbers. Even numbers are multiples of 2. Okay. When you see sine of whatever x or cos of whatever x to some even powers, and then you need to think about using the trig identities of these two. Now let me copy the trig identities to this slide. For the next few questions, we are going to practice a few questions using that trig identity. I'll put that in on this corner. Perfect. You see, what's good about the identity? You learned that in high school. You probably can remember that. If you cannot memorize, then memorize the identities right now. Okay. What is the good thing about that? In that question, we have cos of 2x, the whole thing squared. We do not have a handy formula to evaluate the integral. Okay. But after using the trig identity, we can change the power exponent from 2 to 1. So later on, in order to evaluate that, all we need is to evaluate the integral on the right hand side. But it's much easier to evaluate the integral on the right hand side. I will tell you what I mean. Okay. Actually, the identity, I can replace x with anything. Okay, it's essentially identity, right? So for any u, so can I give you the equivalent formula? For any u, cos of u squared is equal to half of 1 plus cos of 2u. The same thing. Now for the question on the screen, for number 6, we can apply that formula. Okay. You just imagine 2x as u, and then you apply the formula. I believe you can leave out, you can leave 1/2 the factor, 1/2 out of the integration notation, right? After that, that's ugly integration notation. It's 1/2. Now inside the integral, you use that formula again. You imagine u here is 2x. Okay, so you have 1/2 of, in the integral you have 1 plus cos of 2u. Your u is 2x, so you have 4x here. So that makes sense. 2 times 2 is 4. Okay. Actually, at this point, we can evaluate the integral on the right hand side. I mean, we can evaluate that already. Okay. You still leave out 1/2. Now all we need is to evaluate the function term by term. Antiderivative of 1 is nothing but x. You know that the function is a function of x. Anybody want to tell me antiderivative of cos of 4x? What is a antiderivative of cos of 4x? To get antiderivative of cos of 4x, we think which function has the derivative of cos of 4x. Alternatively, you can do something on scratch paper. On scratch paper, you could evaluate the integral of cos of 4x. You could set u to be 4x and so on. But we mentioned before, what is a antiderivative of cos of 4x again? We just did that last class, when we talk about integration by parts. What's antiderivative of cos of 4x? So please write something down in the chat, please. It's sine of 4x. It's not quite right. There should be something before. Yeah, that's right. I think that's right. 1/4 of sine of 4x. You just think which function has the derivative of cos of 4x. As long as you know the chain rule, then it's easy to get that. Okay. You could leave the final answer like that, or I could give you one more step. You have 1/2 of x, 1/2 times x, and then you have 1/8 times sine of 4x, and then plus c. We mentioned before, it's always possible to to check your answer by taking the derivative of your answer. If you can return to the integrand, I mean, if the derivative of your answer is the integrand, then the answer is right. Okay. That's number 6. Again, the two identities can be used when in the integrand you see sine of x, sine of whatever x, cos of whatever x to some even powers. I still leave the identities on top of on this corner. And then we'll do this thing to the power 4. After that, you do number 8. That's your in-class quiz question. Okay. I'm going to do this. You see, we have cos of x to the power 4. Actually, if you replace x with 2x, 5x, or whatever x, it's essentially the same thing. I think we can just do this. To the power 4 to some even power. Whenever you see something to sine or cos to some even power, you think about one of the two formulas. Okay. The formulas are for sine of x, the whole thing squared. But here you have sine of x, the whole thing to the power 4. So before you use the formula, you have to do a little bit of work, okay, so that you can make use of the formula. You know it's okay. A to the power of m and then to the power of n is equal to, anybody want to recall a property you learned in high school or junior high school? Yeah, probably that's before junior high school. A to the power of, this time you have m times n. No, so this is not in class quiz. I'll go over this. The next question is going to be okay, a to the power of m times n. Okay. So this is the case. Using that formula, you can convert cos of x to the power of 4 as cos of x squared and then squared. Right. Yeah. I think the message has a lag. Okay. So that inside the brackets you can use one of the two identities, the second identity, right? The second identity tells you, now replace the stuff inside the brackets as half of 1 plus cos of 2x the whole thing squared. Watch me, I hope I'm not going to mess up too much. I will continue from here. I'm going to leave out a constant factor of 1/4. So do you know how I got 1/4? 1/2 squared is 1/4. And then the inside part, I will write one more step. The inside part is 1 plus 2i cos of 2x, I mean. The whole thing squared. You multiply out the integrand. Probably I want to remind you one other formula. A plus b the whole thing squared can be expanded as a squared plus 2ab and then plus b squared. If you use that formula, it's easier to multiply that out. Okay, I will continue from here. I'll go from here to here. Okay. You use that formula, so do not forget 1/4. You have 1/4 in here. Your a value, your a is 1, your b is cos of 2x. You use the formula I just mentioned. You have 1 squared, which is 1, and then 2ab. 2ab, I think you have 2 times cos of 2x. That's your 2ab. And then b squared, your b squared should be cos of 2x, and then the whole thing squared. Okay. Now the idea. If you have something to some even power, either sine of whatever x to some even power, or cos of some x, whatever x to some even power, you apply the formula once. And then you reduce the power. By 2 or by half. Yeah, probably by half. But you reduce half of the power. By that I mean 2 is half of 4, right? Now let's say if originally you have cos of x to, now let's say to the power of 10 or to the power of 8, and then in the next integral the highest power would be to the power of 4. I think it's right. Okay, it's easy to evaluate that 1. It's easy to evaluate that cos of 2x. Now the only thing you need to work on is the integral of cos of 2x, the whole thing squared. Okay, probably I need to use one more slide to cover everything, but I want to evaluate cos of 2x, the whole thing squared, separately. Okay, now for the indefinite integral of cos of 2x, the whole thing squared. I do not have to write 4 actually. Probably I want to write where. I'm trying to say I'm going to integrate that term separately. Okay. We can use the formula again, right? So did we get the answer to this question earlier? Yeah, we just did that. Okay. You just repeat this. I'm going to copy the answer to here. It's much easier now. It's a good thing about using computer to write everything. You can copy and paste, right? We did the question from the earlier question. Okay. Now all we need is to integrate the integral, so term by term. Now the given integral cos of x, the whole thing to the power of 4. Now I'm ready to write the final answer. Okay, it's 1/4 of, for the stuff inside the brackets, I'm going to integrate term by term. Antiderivative of 1 is equal to x. Antiderivative of cos of 2x, I think Ben just told me, is a half of sine of 2x, right? Multiply that by 2, you'll have sine of 2x. Right. And then the integral of cos of x, the cos of 2x, the whole thing squared is here. It's just that I'm going to copy everything from here, and then plus x over 2, and then plus 1 over 8 sine of 4x, and then eventually we're going to plus c. If you want to write the answer in slightly better form, I will write the better form of the answer on the X screen. Okay. Okay, x plus half of x, I believe is 3 over 2x. So multiplied by this 1/4. Three over 8x. I was trying to say you combine the underlined two terms, together with the factor of 1/4. You have that. And then you have 1/4 of sine of 2x, 1/4 times that, over 4. I think you have 32 in here, right? 4 times 8 is 32. That's the better form of the final answer. It doesn't matter. I told you, you do not have to simplify. As long as you have any of the two forms, it doesn't matter. It's right.